Everybody mute. Hey now, you're listening to the VoIP Users Conference from the IP Communications and VoIP community. We're at vuc.me on the web. We'd like to extend our thanks to Synwood.com. Synwood's API can turn a developer into a telco. Our hosted PBX and support is provided by OnSIP.com. The website is hosted at Bluehost.com. Where would we be without ZipDX, full-featured HD audio conference bridge? And local rate dial-ins provided by Voxbone.com. And of course, thanks to all of you participants who make this worth doing. Very cool. Thanks, Michael, for the roll-in. This is going to be a really interesting show. It's already really interesting because we just had another show before it in a Google Hangout. I see that we're live, though, on live.vuc.me. We are also live on Mixlr, mixlr.com/VoIP users for audio only. Having seen that, I'm saying this for people who in Germany, having seen that I know we're live on live.vuc.me, I hope that we are also watchable in Germany, and I'll be getting a report from somebody soon, hopefully. So we're talking Bluetooth Low Energy. In fact, we've got the co-author of the book, Getting Started with Bluetooth Low Energy, Carlos Kufi. Carlos, welcome. I printed out, I went to bluetooth.org because I remember, here's how old I am. I can remember being in a showroom for an IP camera called Axis. You guys have probably all heard of Axis. And remembering that one of the people said, oh, you know, there's this technology coming that's wireless. It's called Bluetooth. I go, Bluetooth? You know, so I first heard of Bluetooth. It was probably, I'd say 98, 99, which is when it was pretty much invented, I guess. So I went to Bluetooth.org to take a look at this, and I see that in the year 2000, according to their site, the first mobile phone with Bluetooth technology came to market. Carlos, you were actually started working in 2000 or 2001 with Bluetooth, right?
That's right. And it's kind of funny that you mentioned Axis, because Axis at the time, they were one of the pioneers with Bluetooth. And in fact, they were the first company to actually release an open source Bluetooth protocol stack that ran on Linux at the time. And that was way before Linux actually had any built-in support for Bluetooth. And we actually tried it and tested it and even considered it for the company I was working back at the time, which was Parrot. And as you mentioned, around the year 2000, it was when Parrot really started getting involved with Bluetooth, as well as many other companies. And we back then opted to develop our own protocol stack, as there wasn't that much, and what there was, which was Axis, wasn't really going to work for us. So it was really interesting. Then Nokia and Ericsson started releasing mobile phones around that time. And about a year later, we released the first hands-free car kit, which would be the first of many, now probably always come built in with car. But at the time, it was an aftermarket option that one could buy.
Okay. And, you know, I usually when we have folks on, we like to find out a little bit about how they even got interested in technology, period. What brought you into computing or technology in the first place?
Right. In my particular case, it was graphics, 3D graphics. In fact, I started my career as an engineer very early on when I was around 15 or so, when I discovered these amazing 3D demonstrations, 3D demos that people were developing at the time using computers that now probably young people haven't even heard of, like Amigas and Commodore and other Commodore models, and later on the PC. So I started off by writing a lot of 3D code and routines and even operating system level code in assembler back then, and I decided to pursue that interest into so I went to university and got a degree. And later on, I switched to networking just because Parrot at the time happened to be there and happened to be working on personal area network type connections, and that's what led me in the end to Bluetooth. And I haven't left it since then because it's been a wild ride this last 15 years or so for Bluetooth, and for me personally. It's just the technology has evolved a lot and has gained a lot of momentum, and even more so now perhaps with the introduction of Bluetooth Low Energy about 3 years ago, 3.5 years ago.
Well, you already answered my first question, so we can move on from then. But also, let's talk about the book a little bit. How did the book come about? Were you contacted? You're a specialist in Bluetooth, so who started the movement on the book? And tell us a little bit about that, and maybe name the other authors also.
Sure. Yeah. Actually, the book, I came late into the book writing process because what happened is, I think, if I'm not mistaken, O'Reilly had decided that this was a subject worth investing in and worth writing a book about. And then they contacted people that they knew, so the editor and the people in charge of new projects that O'Reilly found about several other people, the other three authors, in fact. And then when it came to me, it was really a coincidence that I was working at the time on a project with Kevin Townsend, who is another of the co-authors of the book, who at the time was working as a consultant for ARM, and we were working together with ARM for a very interesting project they have called Embed. And then Kevin basically suggested that I actually participate in the book as well. So that was really great. And the funny thing is, we haven't actually met each other, the authors. I mean, I think that's when I think Akiba lives in Japan, and then Robert, I think, lives in the West Coast, and then Kevin in Paris, and me, I am currently in Germany. So we've never really met, which is, I think, kind of surprising for the amount of work that we've put into this book.
Indeed. You mentioned Bluetooth Low Energy, which is really our topic, and that's the book is what we're going to talk about. But before we do, maybe just a tiny bit of history. So you said that it was 3 years ago, and that was what I was going to ask about, that Low Energy came out. Let me get this straight. Low Energy, really the reason for Low Energy is so that we've got this little background thing that doesn't take too much power running, and we can talk to, like, here, I've got a Fitbit bracelet, for example, that doesn't do a lot, but it will sync with the web database, and I assume it uses Bluetooth Low Energy because it didn't work on my old phone.
It does, yeah.
But the point of Low Energy, I mean, besides the obvious low energy, in the words, the point is that there's a need. You can't just have something running all the time that's taking normal Bluetooth. So the original Bluetooth, we must deduct, took too much power, right?
That's right, yeah. So the original Bluetooth was mainly designed with two use cases in mind, which was audio and more specifically mono audio, that is, low data rates for perhaps 64 kilobits per second, around that ballpark, and then file transfer. File transfer across devices in the vicinity. So that would be, for example, a mobile phone and a PC. The problem is that things changed over time, and classical Bluetooth, as we usually call it, those who are involved with Bluetooth Low Energy, What happened is that Wi-Fi replaced pretty much anything else for file transfer, since Wi-Fi is so ubiquitous now and everybody has a Wi-Fi capable router at home, and therefore it didn't make sense anymore to use Bluetooth, since the bandwidth never caught up with Wi-Fi and other technologies. And for voice, it's remained the main use case and the main interesting point of classical Bluetooth, and the one that's used the most all over the place. But people wanted as well stereo audio. So that was started, and it was sort of bolted on initially because the whole protocol stack wasn't really designed for it. But with time and with several revisions, now it works very well. So then people realized, several people, but more specifically Nokia, back in the mid noughties, I believe, they started realizing that for sensors, small sensors, just like your Fitbit there, or perhaps a thermometer, or perhaps let's say other sorts of temperature or weather sensing devices. For those, you needed something, a technology that would perhaps not send the data as fast as Bluetooth could, and obviously not as fast as Wi-Fi, but with a small battery, it could actually last for months or even years. And that was the motivation behind Bluetooth Low Energy. Small devices transferring very little amount of data, but whose batteries you really don't have to replace. You can forget about. That was the whole thing. So that includes as well mice, obviously, and keyboards, which are pretty suited for the Bluetooth Low Energy standard and baseband and radio. So all in all, there was this, Nokia felt that this area was not covered by any technology, and they did what any good big manufacturer does: invent a new standard, and they came up with this thing called WiBri. But that, as Nokia was slowly having its own problems with the other divisions they had, they decided to join forces with Bluetooth, with a Bluetooth special interest group, and that's how BLE was born. The technology from WiBri, internally developed by Nokia in cooperation with my company, actually, Nordic Semiconductor, because we worked together during those years, and that was then incorporated in 2010, late 2010, into the core Bluetooth specification.
Okay, and I know you have a presentation you're going to be ready to show us, but before you do it, just a quick question, which is throughout the history of Bluetooth, and I've always been curious myself about the speeds involved of Bluetooth, and is there a difference in low energy speed? Data, I'm talking data speed, obviously. And also, if you know, otherwise maybe somebody else can type it into IRC, how it compares to USB, because the average person often has a choice between using Bluetooth, not necessarily LE, but Bluetooth and USB. And I've often wondered myself, which is faster. So what about LE and what about Bluetooth? Are they the same speed or is there a difference?
They are not really the same speed. Classical Bluetooth has essentially 3 data rates that one can negotiate when establishing a connection. That's 1, 2, and 3 megabits per second. So that's not very much. But with BLE, there's only 1 data rate at the moment, although the spec may evolve in the future, and that's 1 megabit per second. But on top of that, you've got obviously the overhead from protocols. So there is a substantial difference between the modulation bitrate and the actual user data throughput. And that difference is perhaps, or is definitely slightly more acute in Bluetooth Low Energy. So you would see that effective application throughput for today for a BLE application can be measured in the low or around 128 kilobits per second. That's real data coming through. But obviously, Bluetooth Low Energy was not designed for that. So USB 2.0, I believe, is 480 megabits per second. So that's way higher than, much higher than Bluetooth.
Okay, you and Michael answered at the same time. Let's see if we can get to, you have some slides, right?
I do, yeah. So let me, that's right. So let me just share this here.
While you're doing that, I have no idea that USB 2 was that fast. That's interesting. It doesn't seem to be a lot of times on some practical applications.
Let's see.
Is that USB high speed or USB full speed, USB 2.0 that you mentioned for you?
Why? Is there a high speed? What do you mean?
Yeah, there used to be USB 1.1. I think it was 1.0, then there was USB 2.0, And then the brilliant marketing people at the USB Alliance or whatever, they basically decided they were going to rename the old standard to USB, I think it was high speed, or full high speed, and then USB 2.0, the faster speed was going to be USB full speed. So one was high speed and one was full speed. And I, to this day, can't remember which is which. And to this day, I still, I still just
Technically,
rack my brain trying to figure out why they did that.
the marketing standard says that USB 3.0 is referred to as USB 3.0 super speed.
Okay. So, so what's faster, high or full? And
I think high
know
is,
the answer, I
is
don't.
faster. I think full is the one that keyboards and mice use, if I'm not mistaken.
I see.
Okay, let's get back to Bluetooth. And Carlos, you've got your presentation there, and we do see a slide. So
You do? Okay, great. I think there's a small delay when I switch slides, so I hope I'll try to wait a little bit before start talking about the new slide. So I put together a few slides just to give you a bit of an overview of what Bluetooth Low Energy is, why, actually we've talked a little bit of why it was introduced, but I'll talk a little bit more about that.
Sure.
And also what it can accomplish in terms of use cases. So there's a few, and some of them may be interesting to our audience. So I've tried to cover as much as I can with the amount of time I have. I also have some additional slides in case there is interest to go further down, to dig down deeper into the actual technology and the protocols. So let's start. So I've already talked a little bit about the origins and how it all started back in the late 90s and in the early 90s. But the Bluetooth itself, it was an internal project based on Ericsson's research. They wanted to come up with a way, as I said, to transfer data between devices in the same room. So there was an interest for that, and they saw a potential for technology for that, and they wanted it to be short range and low power. Low power by those days standards, and by low power they always counted on a rechargeable battery running on a mobile phone or perhaps a laptop. So they had a little bit more leeway than we had when working on Bluetooth Low Energy. So for many reasons, and the state of the technology at the time, they had to pick a band, and even today it's not difficult to find a new technology that uses the same band because it's so ubiquitous, and it's basically available in all countries, which is the Industrial, Scientific and Medical band, the ISM band, 2.4 gigahertz. So they actually, because that band was already busy at the time, they had to find a way to make the technology reliable. So they used frequency hopping, so that you divide the available bandwidth into channels, and then you hop according to a random sequence that's defined by one of the peers, or actually negotiated by the peers in some cases. And then both peers, they jump in sequence so that each packet is transferred in a different subband, so that if one is busy, say because a microwave or a Wi-Fi device or anything else is currently transmitting there, the packet can be then retransmitted in a more available chunk of frequency later. So in 1998, they formed this forum or special interest group, and it's grown huge. As you can imagine, Bluetooth is nowadays a well-known technology. At the time, there were many dissonant voices, and there were many people that were doubting that the technology would have a future, including us at Parrot. We were working at the very beginning. We didn't really know if that technology was going to establish itself as a standard, if people were going to implement it, even though Ericsson, which was a huge player in the mobile space at the time, by the way, was backing it. So, time has shown that there was really a demand for Bluetooth and the functionality it offers. So there's been a huge mounting curve in terms of shipments in those 15 years, and specifically those last years. This since the introduction of smartphones and later on tablets, Bluetooth has proven to be the only technology used for, especially for heat devices and audio transfer. So no one wants a proprietary technology, but with the new devices which don't have USB ports, you can't have a proprietary technology because you cannot plug a dongle anymore. So you need the standard, and that's where the gap that Bluetooth has filled really. So at Nordic, we became one of the board members, which basically have a little bit more power over the destiny and the evolution of Bluetooth over time. And you can see the list of companies that make up this board. It has been, though, it has been difficult, as it is in any other forum or group that's composed of many companies, to get to agreements. And but I think the mechanisms that are in place today at the SIG make this relatively rational and forward-looking process. So pretty optimistic about the future. So let's take a quick look at the revision history. So what is Bluetooth and how it has evolved. I've skipped one of the revisions, which was 0.9, which was never really implemented except for a few companies. So the first real one, the first that got a little bit of wide adoption, was 1.1, which was that 1 megabit per second, the same as BLE today. And that had quite an impact, especially because mobile phones started, as I mentioned, providing support for Bluetooth. And that meant that people started getting a little bit of knowledge about it. They heard about it, and the first accessories started to appear, especially headphones. They were very popular at the time. If you remember the Bluetooth headsets that used to feature in most films, and at the time, it was quite popular and useful, by the way. So. Then the Bluetooth SIG decided to try and pursue the file transfer scenario a bit further by adding higher data rates, 2 megabit per second and 3 megabit per second data rates. But that didn't really turn out well. The Wi-Fi was by then already in the rise, and those data rates really couldn't compare with Wi-Fi. So that never happened, but they tried. Then in 2007, they had something which was relatively important given the reputation that Bluetooth had gathered up until then, and specifically that it was hard and not very user-friendly to pair devices. When pairing means the first time you use a device with another device, and you had to go through this process where you had to input a 4-digit number on both sides, and it was pretty inconvenient, and also it was unsafe, because it didn't protect against man-in-the-middle attacks. In some cases, there were widespread rumors, and some found it actually reports of hacking, etc. So they came up with this thing called Secure Simple Pairing, which uses Diffie-Hellman and asymmetric cryptography to make sure that even someone eavesdropping cannot store the keys that are exchanged at that point. Then finally, in 2009, the Bluetooth SIG tried once more to go back to that file transfer use case, just as a last desperate attempt, and they did so by adding this alternate PHY. So, what that means is you started your negotiation, you start your connection on the Bluetooth physical layer. When both the stacks on both sides detect that there's a big amount of data to be transferred, they are actually allowed to switch PHYs. So if both, though, obviously through a negotiation mechanism, they can inform each other of the capabilities of both devices. And then if both have Wi-Fi, and initially it was also prepared for other technologies, but that never caught up, then they could switch to Wi-Fi and start the transfer there. The problem with that is that, pretty much everybody else was using Wi-Fi, either Wi-Fi direct or just standard Wi-Fi connected through a router to achieve the same, and therefore, again, that never worked out. But they tried again, and it was interesting. Finally, and technology that really occupies us today is Bluetooth 4.0, now 4.1. I didn't want to add a minor revision, which is not that important anyway, but it is called Bluetooth 4.0 plus HS, high speed, which is there because the alternate PHY feature is still included, which supports then enhanced data rates, the 3 data rates that I mentioned, high speed and low energy. So just a quick look at the terminology, because I've had this question asked so many times that I think it's worth just having a small slide, because people and there are some very clear marketing terms in that the Bluetooth SIG tries people to use, but to get people to use. But the problem is that sometimes technical people also write pamphlets or data sheets or even marketing material, and then this terminology, these terms leak into documents that are really intended for the user and not for an engineer. So BR is basic rate, which is the 1 megabit per second classic Bluetooth data rate and modulation. Then EDR, it's enhanced data rate, 2 and 3 megabits per second. You've probably seen dongles. If you go to Amazon and look for a Bluetooth dongle, you'll probably see BR EDR dongle. That's because they shouldn't really print that, as I mentioned, but it happens. So HS is high speed. It's the capability for the Bluetooth radios to switch to another physical layer when required. And finally, LE. Now, LE uses another physical, not really another physical layer entirely. It uses the same modulation and the same physical layer as BR, but it does use another baseband. So some people call the baseband the physical layer. There's a bit of confusion there. So they can share the same analog part of the radio, but the digital has to be different because both the whitening, the CRCs, and in general the traffic, how the traffic is scheduled and sent over the air is different. So LE, low energy, is the appropriate name for engineers. That's what's used mainly in the Bluetooth specification. Then because LE only devices, and we'll see that in a second, are not directly compatible with BR-EDR devices, with the classical Bluetooth devices, the marketing people at the Special Interest Group came up with this two special names or concepts that they wanted to use to clarify the fact that one cannot connect certain Bluetooth devices with certain other Bluetooth devices. So they came up with this Bluetooth Smart. Bluetooth Smart essentially means an LE device, only LE. That means it only has what we call the radio, but radio really means radio plus baseband. So an LE only radio, and then they called all devices such as a mobile phone or a tablet, which were released after 2010-11, which included both basebands sharing the same radio, Bluetooth Smart Ready. So when you hear Bluetooth Smart Ready, that really designates a device that can connect to both your old Bluetooth mouse, your old Bluetooth stereo headphones. When I say old, could be new as well, but old in terms of technology, old hands-free car kit, and at the same time it can also connect to low energy sensors or Bluetooth Smart sensors. I forgot to mention before I started that if you have questions during the presentation, please do feel free to ask them. I'm very happy to answer questions at any time.
And of course, people can ask questions in IRC. We're on channel VUC on Freenode.net. I'm watching it. Michael's watching it. And even if you don't want to interrupt, just make a note in IRC and we'll ask the question if you can. Go ahead, Carlos.
Great. So I just here I have highlighted the three types of or the three terminology items that actually are BLE compatible or that have something to do with BLE. So what about the configuration? How does that work in reality? So now you've got these three types of devices. How do they communicate? Well, I've got a small slide that actually shows the interaction between these three types of devices, and I hope it can clarify a little bit how they really work among peers. So here we have a classical Bluetooth device. So this is this could be any device shipped between 2000 and 2010. So those are always backwards compatible. So Bluetooth has always been backwards compatible. So anything can work with anything, and a lot of effort has been put into that, except obviously for low energy, because that couldn't be done. The baseband, the data rates, the scheduling for the radio, it simply didn't work for low energy. So they had to come up with something. And what they came up with is the following. So you've got your protocol stack for a classical Bluetooth device. Here you've got the protocol stack for a Bluetooth Smart or LE single mode device. And I'll come back to this single mode a bit later. And you'll see that there are three layers that look pretty similar. So you've got the physical layer at the bottom, then you've got the link layer or link manager, depending on which version of the Bluetooth spec you're looking at. And that's basically the baseband plus the lowest level real-time protocol that controls the traffic at its lowest level. It would be the equivalent of Ethernet if we're thinking in TCP/IP stack terms. And then the L2 cap, which would be sort of an amalgam between TCP and IP, which is the main routing protocol, and also performs segmentation and reassembly and all of these nice things and flow control. So that is exactly the same for both stacks. So then we at Nordic and my company and the book, it focuses on the devices on the right. So that is sensor devices that only support Bluetooth Smart or Bluetooth Low Energy, and that's why they're called single mode, because they only support one mode. That mode is low energy, and that the layers you see on that diagram on the right, those are the only layers they have to implement. But mobile phones, PCs, tablets perhaps, they have to implement both, because they want to be able to connect to your stereo Bluetooth headset and to your sensor at the same time. So what they do then is they essentially share the physical layer, as I mentioned, but they have to split their baseband and their low-level protocol into two. And that's what they do. And they schedule both technologies around one single radio. So they can do that. There's been quite a lot of work put into that, and modern Bluetooth chips can do a lot of nice things around having only one single radio. And then what they have is two protocol stacks running in parallel. One for the sensors with the GAP, GAT, SMP, and ATT. We'll talk a little bit about those. And then the classical SPP and RFCOMM, which are the classical protocols used by Bluetooth, classical Bluetooth. So those devices, which would be your modern Android smartphone, your iPhone, your recently bought PC with Windows 8, or your iPad or an Android tablet, all those are smart-ready devices. They are dual mode devices. So they are devices supporting both protocol stacks. So can take now closer look. I just wanted to highlight that this is the one we'll be concentrating on today, because the other side of the equation, so the Bluetooth Smart Ready devices, they are mostly today dominated by one chipset brand, which is called Broadcom. They have a lot of success, and they are pretty much all over the place. They produce their dual mode chips, and they usually come incorporated in also with Wi-Fi all-in-one chipsets, and they're used in many devices. So we at Nordic, and during the composition of the book, we concentrated on that single mode world of things, which is pretty interesting. So I've already talked a little bit about why we invented Bluetooth LE, but I'll just mention a couple more things that haven't come up so far. As I said, file transfer and audio, that wasn't really never the goal for BLE. So the other problem is Bluetooth chips, they've gone down in price over the years, but they were still relatively complex, and they required quite a bit of RAM. Most Bluetooth standard classical Bluetooth chips, the chipset usually has around 64K of RAM. That may not seem a lot, but when you're shipping millions, and especially in small devices like mice or perhaps headsets or keyboards, that starts adding up. So one of the goals with BLE was a really simple protocol stack. That's why we simplified it. That's why we took away some of the complexity that was there in classical Bluetooth and tried to come up with a scheme that would allow the BLE to be flexible in terms of what data can be exchanged, how fast, etc. But also at the same time, it wouldn't require a huge amount of RAM or processing power. Bear in mind, just as an anecdote, many Bluetooth devices today use chipsets that run on an Bluetooth Low Energy. Obviously, they run on chipsets that use the 8051 core, and that's an old core, and that's an 8-bit core that has been around for decades now. So that obviously that's changing, and most people are now moving to the Cortex-M series of microcontroller cores designed by ARM or other cores in some cases, but there are still several dozens of millions of products out there running on 8051 cores, just to give you an idea, and sometimes with as little as 10 to 12K of RAM. So the other thing is HID, human interface devices. So the Bluetooth HID market never really took off. It never really worked. They tried, and they tried hard. And apart from Apple, which has always used Bluetooth for mice and keyboards, for the rest, most people were actually using other radios and proprietary radios for that matter. And the reason they did that is that Bluetooth, standard Bluetooth, is not great for heat. Heat needs to send a lot of packets, sometimes in burst mode, and Bluetooth had too much of an overhead cost towards setting the connection, maintaining it, and the whole thing just didn't work well. So you were looking at 1, 2, 3 months of battery life compared to more than a year with proprietary radios. So BLE was also designed in part to address that problem, because the heat market is big and SICK didn't want to let it go. So as I said, the other thing was coin cell batteries. So coin cell batteries, that was unthinkable to run a device on a coin cell battery with classical Bluetooth. But on Bluetooth Low Energy, that's actually the most common type of battery. So you run key fobs, you run hearing aids, you run similar devices, all sorts of devices, even keyboards on a coin cell battery, and you run them for years, sometimes 2 years on a coin cell battery. So that's that was something that was never going to be achievable with Bluetooth classical Bluetooth. Sorry. Finally, there was one more factor that also triggered the introduction of or the starting point in the work towards BLE spec, and that was smartphones. Smartphones are everywhere now, and since the beginning, smartphones have been bundled with Bluetooth. So the Bluetooth SIG knew that if they introduced a new standard that was more or less compatible and that would be included in every single Bluetooth chipset, people, or rather handset manufacturers, they were gonna introduce that in their design. So they did, and you can see now it's almost impossible to find a smartphone, a mid to high range smartphone which doesn't support Bluetooth Low Energy and classical Bluetooth. So that worked, and the fact of having an internet-connected device that can then connect to a network of sensors that are always there, that you don't have to replace the battery of them, that on top of that, they can communicate one towards the other through the use of clever meshing techniques if you actually implement that. And all that meant that Bluetooth Low Energy had a big potential, and that's starting to show. I think last year there were some 50 or 60 odd million Bluetooth Low Energy devices shipped. That's not counting phones, obviously. That's just the sensor side or the peripheral side, as up until now it's been called. But that number is expected to increase by a lot. So yeah, so the SICK had some vision there, and they realized it. Took a long time, by the way. It took a long time, but we got there in 2010. So just a few key features of Bluetooth Low Energy. I am actually relatively proud to be able to say that Nordic pioneered this ultra low power, as they like to call it, or we like to call it, wireless communications, because we had been shipping ultra low power radio for years. We had been shipping them to many human interface device manufacturers, big names, and we had almost a monopoly until recently on proprietary radios that could run for years on a battery. Now that applied also to controllers, to game controllers, to even microphones, because we had a version with audio, etc. But BLE has a big advantage. BLE is everywhere and it's built in. So that's why for Nordic as well as for almost every other technology company focusing on low power wireless technologies, Bluetooth Low Energy was the holy grail, really, or has been the holy grail for these last few years. So as I mentioned already, the physical layer is pretty much compatible on all 4.X devices, be them classical Bluetooth or not. And they try to reuse the protocol stack. But really the key thing here is how to achieve ultra low power. It's actually, it's pretty simple, really. That's what most people have been doing to not consume power, to avoid consuming power. You have to race to idle. You have to basically turn off the radio as much as you can. So and transmit as seldomly as you can. So and that's the point. That's the whole concept around which the fundament and the basis of Bluetooth Low Energy revolves. It's being able to have the radio in an idle mode in which it consumes very little power for as long as possible. And that may seem like obvious, but it's really not that obvious when you start combining other factors into it, such as, for example, the fact that you want the memory footprint and the complexity of the stack to be as small as possible, and also you want to be able to establish a connection fast. Why? Because if you can't establish a connection fast, you have to maintain it. Because if your reaction time, which is often the case with classical Bluetooth, is up to 3 seconds, then the user, if it's, for example, a mouse, it has to wait up to 3 seconds before the pointer starts moving on the screen. That's obviously unacceptable. And same goes for a key press, same goes for temperature reading, same goes for many other things that actually apply in real world scenarios. And being able to connect so fast without actually sending much data or as little data as possible, and at the same time maintaining compatibility with the 2.4 gigahertz band, that was we had to come to a lot of compromises there. We had to redesign several parts of the protocol stack and the physical layer several times just to get things right. So that's really that was really the whole point of it, and the whole process was guided by these tenets that will remain true all along the development process. On top of that, the Bluetooth protocol stack was complex. It required a lot of state. It required a lot of maintenance because there were a lot of backwards compatibility provisions inserted into the stack, bolted into the stack, so that everything would work with everything. So the fact of being able to start from scratch, thanks to this Bluetooth Smart Ready sort of marketing technique they used in order to be able to break off from the spec and be able to get a clean slate and design things in a way that really didn't matter anymore whether you had a lot of baggage, you carried a lot of baggage with you. So that allowed us to design a very, very simple stateless sort of key value access protocol for all data items, and that has been key. I think that's been really, really important to the success of the technology. So those are some of the key features. I will just give you a very quick overview of the competing technologies, because it's BLE is not alone out there in covering the necessities of such use cases and scenarios. It's actually a latecomer. As I mentioned already, proprietary 2.4 gigahertz connections, those have been around for a long time now, and they're incredibly optimized for the use case they serve. So mouse, they're obviously, because they're proprietary, you can do whatever you want in your protocol stack. So you design your packets, you design your access control, you design your scheduling, you design your radio timings, you design absolutely everything around your use case, so that it's basically impossible to do it more optimized than that, especially if you're talking about the standards. You have to compromise on something if you want to be able to cover multiple use cases as Bluetooth Low Energy does. Problem, obviously, it requires a dongle. That dongle that everybody hates, everybody loses, and that comes usually bundled with your mouse, but you don't know where it is about 2 months in. And although they're very, very efficient and work very well, everybody prefers a built-in standard technology. So like you can take your mouse and use it with your Android tablet, later with your set-top box, and also with your laptop or desktop computer. So that's great. You've got one mouse that works with everything. And sometimes even sometimes it can even work concurrently with different devices, so that it acts as a sort of a switch. So changing the focus from one screen to another one. So that's got some really potentially interesting use cases there. So ANT Plus or ANT is a very specifically targeted standard, specifically targeted towards sports. You probably heard of it. It was developed by a Canadian company, and it's still currently being actively developed. It's a semi-standard in the sense that it is only guided, and its future is strictly decided and completely determined by the decisions and the steering group that's only within that company, which is called Dynastream. But at the same time, they do publish specifications, and if you join the development program, you can actually write or develop devices that are compatible and have that ANT logo stamped on them, and that will work with other ANT devices. The problem, again, no one from the device manufacturer side of things decided to, or actually decided to bet for ANT. So the problem is that there are no ANT compatible phones out there. There are some actually, but very, very few. So, and remember, as I mentioned today, a bit earlier today, we cannot plug a USB dongle into a tablet or a phone. So, and tablets are more and more gaining terrain over traditional computers. So that's a big problem in looking to the future. Finally, ZigBee. Yep.
No, that's our friend James and Andy who are coming in. Guys, you have to mute yourself. Go ahead.
Okay. Right. So welcome again. So for ZigBee, this the ZigBee standard, this is just a proper standard, just like Bluetooth, with a steering group and collaboration among companies to steer towards the use cases that people or those companies itself believe are useful for customers. And it's a very specific protocol as well. And that this one was essentially designed for industrial and automation purposes. So it's your big mesh network that can cover a full factory, for example, and that can relay information among perhaps industrial robots, perhaps PICs and robots, or even control computers, etc., etc. So it's extremely well suited for those type of applications, but not very much so for the other types that we will talk about today. So again, very practical for certain roles and for certain specific distributions and topologies, not very much so for the one that occupies us today. So it's still very, very much in use, and the ZigBee committee always hoped that it would make big inroads into the home automation market, which is basically a largely untouched market as of today. So today, home automation is it's a very, very precious, let's say, target for many of those standards, because there's no one today that has established itself as the home automation standard. So ZigBee has tried that, and so far with moderate success, but BLE is trying as well. So we'll see what the future brings. This is the situation then in the market today. I'm going to talk a little bit about the architecture of Bluetooth Low Energy, and I'm going to do it in a way that I'm going to start with the use cases first. I'm going to start by talking about how applications are written. Obviously, you can at this particular point, most of the information here is taken from the book, and the book obviously does dig in deeper. But my goal here today was to give you a rough idea on how BLE works and how it achieves communication between devices without compromising on energy consumption. And I'll start with the application and profiles, and then I'll move on to the lower level protocol layers if there's interest, because I have a limited time as well. So for the application and profiles, essentially, I'll talk in a minute about what the profile is, but the application in a Bluetooth Low Energy device, typically in an embedded device that's a single mode Bluetooth Smart only device. It's a small piece of software, usually written in C. Some vendors do provide scripting languages to write those applications in, but for the most part, C, and that interacts with the protocol stack, and that is essentially the entity in charge of communicating with the sensor. In the case, for example, of a keyboard, that would be a matrix that allows you to sample the keys and then translate those into key press codes that are then sent over to the computer or phone. Usually, when you buy a development kit from one of the companies that manufacture chips that allow you to design Bluetooth Low Energy devices, you get two separate things. You get the protocol stack. That's usually closed source. We at Nordic and many other of our competitors, they ship, or we ship as well, a big binary blob, which is the protocol stack itself. But then you get libraries as well, and those libraries come in source form, and they implement the profiles. And I'll go and talk a little bit more on the profiles in the next in the next slides. The Bluetooth SIG never really intended to define a standard API. There's many reasons for that, but everybody then has obviously had to come up with an API. That's not true for USB, for example, where they kind of decided on an API, where there's no equivalent of sockets, for example, which are pretty much all in every single development platform you can think of. For Bluetooth, you'll unfortunately have to learn a new API for each vendor you switch to. For the host is the core of the protocol stack in terms of non-real-time protocol. So it's the higher protocol layers. It contains everything that's related to multiplexing and data arrangement, flow control, etc. And that piece of code, it's usually written and runs on a mid-priority thread or interrupt level, so that it doesn't interfere with the radio, which obviously always has to have the priority, because it has to comply with very strict timings that are imposed by the specification. But at the same time, it also runs at a slightly higher level than the application, so that the processing is not stopped by the application code. This would be, again, I'm just going to draw that parallelism here between Bluetooth and TCP/IP world, and this would be, again, TCP and IP pretty much, with HTTP thrown into it for good measure, because the equivalent of HTTP would also be there. The controller is really your Ethernet driver. If we again continue with the metaphor, it's the hard real-time part of the stack. It drives the radio. It does the scheduling, the connection management, the time, the hard real-time timing. It controls absolutely every single packet that goes out and comes in. And it also is obviously instrumental to the low power features of the stack. So it is it that allows the rest of the stack to go to sleep. And it's the one that wakes up the whole device most of the time. It also includes the hardware acceleration modules and analog radio, obviously. And the hardware acceleration, it's important because Bluetooth Low Energy uses AES, the AES encryption standard, and that's done in hardware on all devices because it's transparent. The AES encryption in BLE, it's enabled, and the keys are negotiated using a very specific protocol. But once the keys are there, you give the keys to the stack gives the keys to the radio. And then the radio is the one in charge of automatically and transparently encrypting and decrypting all data traffic that goes over the air. This slide is interesting because if you ever plan to do any Bluetooth Low Energy development, you probably have to make a choice. And this choice boils down to essentially three possibilities. One is system on chip, and that's by far the most popular today. Almost every single vendor out there offers a system on chip option, and it's quite easy to understand why. You wanna manufacture a device, and you want to reduce your BOM costs. You want to simplify your PCB. So having one single chip is fundamental if you wanna achieve that goal. So in an SoC, you've got a single memory space, usually flash, but can be ROM as well, with the application, the host, and the controller. Everything runs on one single chip. There's also the dual IC over HCI, where the application and the host run in one CPU, which is typically a bit more powerful. And then you've got this HCI. Now, HCI stands for host controller interface, and it's a standard. It's a standard serial interface that can run over USB, UART, or even some other transports that are there, such as SPI. And this standard allows a host and a controller to communicate seamlessly. And you then obviously switch controllers from another vendor, and that will work. That's interesting in some cases where you are heavily invested into a host, or you want to do things that perhaps are outside of the spec, and you don't want to reuse the host libraries that are provided by a vendor, and instead you write your own, but you don't want to write the lower layers, the link layer, etc., and the radio, obviously. And finally, the one that's mostly used by phones and tablets, and not really very much for embedded devices, but sometimes they do. In fact, the bracelet you just mentioned, the Fitbit uses that dual IC mechanism. It uses the 8001 Nordic Semiconductor connectivity device, and it has a very specialized microcontroller which acts as the main CPU and contains only the application. So we have this proprietary protocol that allows an application to control the full protocol stack over these an SPI in this case. And that allows very specialized microcontrollers to not have to have anything to do with the wireless protocol itself. And for example, this is a model that's quite popular with watch manufacturers, because watch microcontrollers have been honed and refined over years to provide absolutely stellar energy consumption while driving an LCD screen. And people don't want to replace those CPUs. The customers don't want to replace them because they're so optimized and there's so much work has been put into them. So instead, they prefer to add a second chip that runs everything that has to do with the radio. So this is actually a bit, it has become more popular than anybody expected, really, although the system on chip option is by far the most popular. So a little bit of operating system support today for Bluetooth Low Energy, because I think it's worth mentioning how all in most vendors have gone with Bluetooth Low Energy in terms of supporting it in their operating systems. So Windows XP and Vista, unfortunately, and 7 as well, unfortunately, were deemed perhaps not juicy target enough for by Microsoft to include native 4.0 and therefore low energy support in them built in. So what they did then is they rely on the OEMs, so that's the people building the dongles and the chipsets to supply their stacks which support low energy. So today, if you buy say a laptop with Dell and it comes with Windows 7, Microsoft doesn't have support for low energy for it, but your Broadcom or Toshiba, whoever has shipped the chipset, will replace the default protocol stack that comes with Windows with 4.0 compatible stack. Windows 8, on the other hand, supports fully Bluetooth Low Energy as a Bluetooth Smart Ready device, and so does Windows Phone from 8.1, from version 8.1. For Apple, they were early adopters. They were the first ones to adopt Bluetooth Low Energy, Mac OS 10 or Mac OS X of version 10.6 and above, and iOS 5 that really were ahead of the curve with Bluetooth Low Energy. That has been a long time now, and they support it in all their computers and tablets and also phones. Finally, Android, they came a little bit late into the game. They had been implementations out there, but they were implementation by the vendors, so by the device vendors, that is Samsung and HTC. When finally Google came around to add support, that was we're already at version 4.4 of Android, and they used this BlueDroid stack. They replaced the standard Linux protocol stack with BlueDroid. Many reasons behind that. I'm not going to get into that now, but it's an interesting conversation. And today, most devices ship with 4.4 and above and fully support Bluetooth Low Energy with a standard set of APIs. Finally, Linux, it has supported BLE for a long time now, and it will obviously continue to do so in the future. In fact, most of the investment and coding today and the commits that come into the standard vanilla Linux protocol stack come from BLE contributors. Just a quick overview of how the architecture looks on a BLE device, and then I'll talk a little bit about use cases, because I don't think I will have time to go into each layer separately. But just to give you an idea on how the host, the controller, and the profiles are split. Profiles are defined by the special interest group, and they're essentially use cases. You could see these as the USB classes. So you've got this mass storage device class, and you've got your heat class, and you've got your audio class. So that worked well with USB, and it's also worked very well for classical Bluetooth. So for BLE, they've done the same. They've taken standard use cases that they knew would be useful to many users, and they defined themselves how one should interact to implement that use case directly in the specifications issued by the working groups. So you've got many use cases, and there's many more coming, because there's many working groups today working on Bluetooth Low Energy profiles. But we'll see a few examples later on. Those the advantage, obviously, of having a standard profile is that you get interoperability among vendors. So you can use your temperature sensor with any other device that supports collecting that temperature from you, and regardless of what the vendor was The host, I've mentioned it already. We'll see if we'll have time to get into that. And then the controller got that interface. We talked about the link layer, which is the low-level protocol, and the physical layer. So I'm just going to tell you a little bit more about profiles, because I really wanted to show you use cases, which I think are very interesting. And they're perhaps, there's a lot of Kickstarters today, Kickstarter initiative or campaigns being started around Bluetooth Low Energy. And some of them are quite ingenious, and they are, they come up with ideas that are very interesting. And these profiles give you an idea of the type of things you can do with BLE. So a profile is really a slice. And when I say slice, it basically means it tells you which part of each protocol you need to support to implement this use case. That's exactly what it means. So protocols are big and they're complex, and sometimes a use case is simple. So you don't need to support everything. So you can reduce your RAM, you can chuck half of your stack away if you want, and you can keep only the key essential parts of the protocol stack you need to actually implement the use case. That's very useful if you want to go mass production, you want to reduce the RAM, you want to reduce the ROM or the flash. You can actually do that thanks to the profiles, because when you want to start selling that device, you'll have to qualify it, obviously, just like Wi-Fi and Bluetooth, and USB does. You have to undergo a certain qualification procedure, tests, etc. But only the features of the profiles that are actually relevant to the profiles you claim compliance with will be tested. So that's a way of heavily optimizing and aggressively optimizing devices for mass production. We'll talk about GATT a little bit later, but what it also defines is the roles and the procedures and also the security requirements. That is key, so that if you know that one device, which is the one providing temperature, for example, if you've got a temperature profile, always has to act as a peripheral, and the central, which is the device that initiates the connection, always is the one collecting that temperature, there will not be issues when connecting devices that implement that. So that's defining the roles in a very detailed fashion, and the procedures to obtain that data is key to that interoperability that we want to achieve. Right, so let's go over a few profiles, because I think that would be of interest to most of our audience today. We've talked about heat over GATT. We've talked about heat and heat over GATT. GATT is the generic attribute profile, sorry. I haven't introduced that, but I had to rearrange my usual order of introduction of concepts so that I could cover as much as possible without going into detail. So this is essentially your a host. You've got a host, which is always a PC, a tablet, a phone, or anything that can receive input key codes, and a device, which is the keyboard, the mouse, the trackpad, anything that can detect with a sensor and issue then to the host those press codes or whatever they're called, and the various standards that are there. It's important though to note that heat over GATT reuses the USB heat standard and maps it. All it does is it takes that standard and it maps it over to the Bluetooth protocol stack. So if you've got a mouse that's already heat compliant, it should be pretty straightforward to move over to Bluetooth, because they did that on purpose, obviously, because USB was already so big on heat. Heart rate, and heart rate has been also a big success story for the special interest group. This is mainly targeted at people wanting to measure their performance while practicing sports, or even for medical purposes as well. So medical is another big area in which the SIG is investing and trying to gather interest from. For heart rate, it's a very simple scenario and use case where the heart rate sensor measures and usually averages the data over time, and then at regular intervals, and that's usually once a second, it sends a reading from the device to the mobile phone or to the collector, whatever that is. This profile is particularly descriptive and representative of the whole BLE mantra, because if you think about sending one piece of data which contains a few dozen bytes every second, devices running on these can typically run on a coin cell for years. while sending data 8 hours per day sometimes. So this is the typical use case that was a goal and was achieved by the specification. You've got proximity find me. This is interesting, although we haven't seen mass adoption yet. This is all about having a key fob that can locate devices. So typical use case would be having your phone, you forgetting your phone, for example, on the table in a bar. Then you leave the bar and you've got your key phone, your keychain with your keys that starts beeping, alerting you that you've gone far away from your phone. This obviously also works for pets, for example, keeping your pet in range if you leave it unleashed in a park, or even alerting you when you leave the house if you're forgetting your keys, so your phone can alert you. This sort of proximity and close range scenarios. There's also the fact that you can press a button on either device to force the other device to start beeping. So that allows you also to locate devices. So again, those devices, very tiny devices, coin cell battery, year-long battery life. This is the cycling and running power speed cadence profile that's directly targeted at fitness and cycling. So it's all of those sensors you can place on your bicycle or even on your treadmill to monitor and gather data about your performance, about your improvements, about your curves, anything that can help people then have an idea of their evolution in terms of fitness levels. So those are, again, very popular. Alert notification, this has been as well popular. And these essentially relays notifications from a phone or a tablet into a wearable device, be it a watch or be it, for example, a sort of smart jewelry, as some people call it, where you would have something vibrate or light up when you receive a certain type of message. So again, practical for everyday life and running on very small batteries. So this can popular as well. There's iBeacon as well. You probably heard about iBeacon. I know that O'Reilly has an iBeacon book which is going to be released soon. And iBeacon has been extremely popular and a little bit all over the place in the press lately. And the reason behind that is that it kind of breaks into a use case that almost no one had attempted before at this scale, and it has the potential to become the next big thing, or at least one of the next big things. It essentially consists in taking sensors, placing them at certain locations in a building, say a shop, for example, and sending unidirectional packets from that beacon, from that device that's typically battery powered, that can be stashed somewhere in a drawer, or perhaps into even into a display, in a shop display, anywhere really you can think of, a museum, for example. And then that device sends at regular intervals, typically 10 times a second, so every 100 milliseconds, it sends a beacon packet, an advertising packet that contains just a UID and a couple of numbers. And what that achieves is that the application, if the right application is installed on the mobile device, when you go across into a certain area, an iBeacon region, as they call it, it can alert you of a lot of types of useful information depending on the context. So, for example, in a museum, it could give you information about the painter, or background about the paint itself, the history perhaps, etc. Then, if you go into a shop, it could alert you about offers or discounts, or even be used for indoor location. So, if you've got a map and you know the exact location of each of the beacons inside of a building, it could, to a certain extent, obviously, and not with very high precision, although there have been experiments where they locate you within 1 meter. Don't quote me on that. This application can actually tell you where you are anywhere, really, as long as it's the area has been installed or has had its beacons installed. And the thing is, this can be extremely useful in public places, railway stations, or even airports, etc. I know people have been talking forever about this, but this is the first time that I personally, and I've heard also, and I'm also skeptical because I've heard it so many times before, but this is the first time that I see it as actually possible, because BLE uses very little power. It has almost no impact on your phone's battery life, just scanning for those advertising packets. And it's everywhere now. It's in every single device. So it has a lot of potential. Then I was also told that many people in the audience would be interested about audio. So I made sure to include a slide about that. Audio over BLE. Now, this is a bit special because audio over BLE is not part of the BLE spec. It never was. I don't know if it will be in the future, and perhaps, but right now it's not. Now, and BLE itself was never designed for audio. I mean, audio is the exact contrary of what BLE stands for, which is turning the radio as much as you can. If you think about audio in terms of flushable isochronous traffic, that's really not what BLE was all about. BLE provides a reliable transfer that will resend the packet as many times as it's necessary just to get that packet through and then be able to switch the radio. So now, there was a company, Apple again, that decided it would be useful for hearing aids, because hearing aids have a tiny battery. So what they did is they added proprietary extensions to the baseband, not to the radio, but to the baseband. There's really not much I can say about it, because although our company is part of the Made for iPhone program, you're obviously not allowed to disclose. So I'm only allowed to disclose things that have already been made public. And the thing about this is, the whole goal behind this is being able to mix together a hearing aid with a hands-free kit or with a hands-free headset without compromising on battery life. And the latest version of one of the hearing aids that support it actually even support stereo streaming. So they connect to both of the hearing aids and stream one channel of audio to each of the hearing aids, and you get stereo audio streaming. So it's pretty interesting. It's already there on the market. Again, not a standard. Maybe one day it will be, but definitely worth looking into and checking it out if you're interested into audio, because according to reports, this actually is pretty good in terms of battery consumption and energy saving. So definitely an interesting area. So
battery, no, just to jump in for a second, battery consumption really is the important thing, because there are so many demands on batteries. And the last blurb, the last rumor I saw about the newer iPhones is that they've got bigger batteries. We're going to have bigger and bigger batteries. So it's one of the interesting things about BLE is that it recognized fairly early, 3 years ago, that, hey, we have a problem here. We need to do something to allow communication with low energy. So that's interesting.
Yeah, it is. And one thing is obviously the battery in the phone, which is important as well. But the battery on those hearing aids, if you've ever seen one, you'll see that they are tiny, and they're tiny for a good reason, because they have to be discreet, among other things, and they have to be very light. So you can't afford to have a technology like classical Bluetooth on one of those. You would basically run out of battery in minutes or perhaps a few hours. So that was the first time in which, or recently was the first time which it was practical to actually put a stream of audio to a hearing aid without compromising on battery. So, yeah.
No, I was going to say older, and maybe some of you have seen this, but older hearing aid technology, you had a little twisted pair of wires going down into the person's pocket because they had to have a rather large battery to run the thing at all. But we're talking a few years ago, but
yeah, I've seen those. And some of them were Bluetooth actually. So you'd have a bigger device with a bigger battery with a Bluetooth bridge that would then plug into the hearing aid. So that has been relatively common for hearing aid users up until now.
Okay, we have a bunch of questions, but have you finished with your presentation yet? Not yet.
Well, I've had one last slide that I would like to present, and then I see that I won't have time to go further deep into the protocol stack, but that's okay. I was counting on that. So I would just want to show you this last slide about the Internet of Things, because there's been so much talk again in the press about the Internet of Things that I think it was worth mentioning it and giving you an overview on how it works. So Internet of Things is a fancy term to describe essentially a sensor connected to the internet. So the nice thing about that is obvious. The benefits are obvious. You can see the state of your sensor anywhere in the world by simply connecting to a certain URL. Now, in the case of Bluetooth Low Energy, this has been also one of the goals, and there are several ways of achieving it. And I'm just going to describe a little bit how to how one could achieve that in several different with using several different approaches. And it's quite interesting actually what they've come up with. One is a RESTful GATT gateway. Now, what that means really is that you leave your sensor as it is, you change nothing, but you have a gateway that obviously is IPv6 enabled, and that periodically triggers polling into the sensor and then relays the information over the internet. Now that's quite an obvious way of doing things. And then you have your sensor, which is BLE enabled. And if you're complying with one of the standard profiles, you don't need to change your sensor code at all, because the gateway will implement the same profile. There's also this HTTP proxy service in which you incorporate HTTP awareness into the Bluetooth Low Energy stack, but only in the measure that you have to know about the URL and also the type of data to push, but you don't need to write any IPv6 code inside your sensor. So your sensor essentially uses the same protocol stack, using the same GATT protocol to transfer the data, but there's certain particular spots or data items that it can write to say, now send this to that particular URL. And that there's obviously need also for a gateway in this case, which is able to bridge HTTP and BLE. Finally, there's IPv6 over BLE, where the sensor is fully IPv6 enabled, uses this 6LoWPAN standard, which has been around for many years now and has a BLE transport adaptation standard. So and in that case, the sensor itself is a TCP client or server and HTTP as well, and it handles everything internally. There's also, very recently, a few months ago, I think maybe a couple of months ago, Google started an initiative to provide JavaScript access to BLE. Now, that's quite interesting. So they've probably heard about WebGL or other initiatives that were started by big players in the industry to give JavaScript access to certain parts of the hardware. But in this case, it would be Bluetooth. Now, in that case, obviously, that your sensor would also remain unchanged, because as long as your computer is near enough a sensor, your JavaScript code could access it directly over BLE. So pretty interesting. So I think this concludes the slides that I had prepared for you. I had more, but as I said, I'm running out of time. So I think we could give into questions. I've got a lot of other things to say, but I really prefer you asking me the questions so that we cover the relevant information.
The way we could do this is we can come back. You can come back in a while and do another session. This has been fascinating, and we do have a lot of questions. I want to remind you to toggle the slide share so that I should put myself on too. For the same thing.
So you can see me? Yeah.
So that we can see you. Yeah. So
sure. Yeah. I'll do that now.
Share. I think our star questioner is with us today, and that's Carl Fife. And Carl is on the bridge. He needs to either talk on ZipDX or talk on the Jitsi section. Carl?
Yeah, I'll talk on the bridge.
Yeah, it's probably better quality. And let me remind you,
exactly.
Carlos. Let's. I'm still seeing the slide. Can
you are? I've switched to video. That's surprising.
Uh-oh.
Okay.
Michael, what are you seeing?
I am seeing his video now.
Oh, okay.
So
There's something on my end. Okay, just please go ahead. Carl, you have a question.
Okay, so first of all, this is just kind of an opinion question. Why do you think that that Zigbee floundered in the home automation space? I know that I remember, talking to Zigbee folks at conferences a decade ago, and they were just so excited about all the different applications, but it's only ever gotten a foothold in very specific vertical industrial applications, and so I'm wondering if you have an opinion about why that happened and why Bluetooth, which wasn't, which is now finding its way, like, in other words, they're busting their butts trying to get into a specific space, and basically the Bluetooth specification trips and falls into that space, right? So
yeah, it does.
So why is that?
Okay, so obviously this is a question that probably no one can answer with certainty, but I can give you my opinion. My opinion is that
Sure, that's exactly it.
Yeah, because I was also involved in talks with Zigbee people 10 years ago, just like you, and I saw the excitement as well, and then seen that basically translate into very little over the years. And in my opinion, the reason behind it is that home automation simply isn't a priority for users, or it hasn't been until now, because it has so the fact that you have to modify your home, and the fact that when you build a new home, you have to choose between adding a home automation system or not, and that usually doesn't come at the top of the list of priorities for builders or perhaps investors. So that whole combination of things, it's the fact that there hasn't been up until now a good enough solution to motivate people to do it, and for people perhaps in general, this hasn't been really a problem that needed to be solved quickly and swiftly. It just was something that would be nice to have, but it wasn't as useful as being able to keep your hands on the steering wheel while you drive, and at the same time being able to talk to someone, which was a very, very critical problem to solve.
Do you think there was any responsibility of like when I look at certain other competing specifications in that space, like for example there was Z-Wave and even Insteon and some of these other things, where the standard was more open. Every time I am obviously I'm an engineering geeky type, and I've tried on a number of occasions to implement certain wireless link technologies to automate certain things in our business and in our home. And basically I found that the Zigbee space was very balkanized. In other words, everybody who was using Zigbee didn't want to be interoperable with other people. They only wanted to be it was like they were using the big Zigbee standard, but it wasn't like the Wi-Fi Alliance where Wi-Fi Alliance was specifically, their mission statement was interoperability, whereas Zigbee somehow missed that train. Do you think that was an important factor?
I think in part it was. In fact, you reminded me of something, because I haven't been involved with Zigbee for years now, but I think that they've made strides towards interoperability, but I remember very clearly at that time, so a few years ago, between 5 and 10, there was clear will from a Zigbee standard to do actually what Wi-Fi had done, but in Wi-Fi they had an advantage, is that they only defined the MAC access and the radio level of things, but they had already TCP and IP, and they had HTTP to cover for that lack of higher level protocols. At Zigbee they wanted to do something similar. Yeah, whereas Zigbee,
that's a good point.
They didn't have the equivalent of a TCP/IP stack to cover for that lack of high-level protocols, so there was no interoperability possible. That's one vendor starting defining their own, but that didn't work out clearly.
It's interesting that you say that, because it kind of reminds me of the fact that what I've been seeing in the real world is a lot of repurposing of the 802.15.4 link layer. So you can actually buy 802.15.4 link layer radios, and you can use them in some goofy, unconventional way. You just use them for creating TCP sockets, right? So, so to your point.
And that has worked well, actually, in terms of establishing the radio and having it used at least to a certain extent. That has worked, but not the grand dream of having a standard that you will work with absolutely everything. Now, the other thing is that for homes you need a bridge usually. So Zigbee was never was never even intended to go into phones, and that would mean then a bridge between your either Wi-Fi or Bluetooth towards the home network if you want to control it from the phone. Instead, what we've seen is direct connection. So we've seen light bulbs, we've seen heating systems, and we've seen all sorts of automation type targets being connected directly via Bluetooth or Wi-Fi to the phone, instead of to a central system that then relays the information to the phone. Right.
Yep. That's very interesting. I think you're exactly right. I never thought about that. So so you're calling out the protocol stack, and exactly that happened, right? There's people are running TCP over 802.15.4 and not
exactly
not the Bluetooth protocol stack. Yeah. So okay. Actually, and then I had another good.
No, I just want to mention that Bluetooth has been so strict with interoperability exactly because, in part because of that, they wanted to make damn sure that absolutely everything that has the Bluetooth logo stamped on it would work with every single other Bluetooth device. And to a certain extent, they have succeeded. So you can take your phone and it will work with most cars. It will work, with a mouse, with mice or with keyboards, etc. And that has worked. And I think that was you have to give credit to the Bluetooth SIG for achieving that, as well as the USB as well interest group, because they also succeeded to a very large extent with that.
Yeah, right. So one of the wireless technologies that I've had my eye on recently is the EnOcean wireless technology, which uses either 315 or I think like 800 and something, like just shy of 900 megahertz in Europe. So 315 US, it was 897 in Europe or something like that. And it's not an IEEE spec. It might be some European spec, but it's an open standard in any case. But what I like about it, and I guess my question is, is Bluetooth low energy? I'm all over the place here. What I like about it is EnOcean is so low power that you can use things like native energy harvesting. So for example, you can have a switch where when you push the button for the switch, that whacks a piezoelectric crystal thing, and that makes a little pulse of electricity, which is captured by a capacitor, then drained off into a circuit, and then that makes enough power to actually send the message. So you can basically have, it's like plug and play. It's like no battery, no wireless. So it's like the best of both worlds. And then they have like motion sensors that are passive solar, and they have, just all kinds of amazing things happen when you get down below that critical threshold. But I'm noticing that it's not getting as much traction as I would have expected, perhaps to your point where it's too hard. People don't care enough about, these automation things. And so I guess my question is, perhaps with BLE having accidental adoption for other reasons, maybe BLE could get into that space that EnOcean is trying to get its way into. And so my question is simply, is BLE low enough power for those kinds of things like passive energy collection, and would it be able to sort of compete in the application space that EnOcean is trying to find its way?
Right. And the answer to that question is people are trying to do exactly what you're talking about now with Bluetooth Low Energy, and some of them have, at least to a certain extent, succeeded. So we've seen energy harvesting companies take license a BLE core and putting it into a chip and making inroads into getting BLE powered chipsets only with, say, for example, movement or any other type of energy that doesn't require a battery to recharge. But this is still at a very early stage of development. So I wouldn't. I could dig it. I think we have a few of customers using our ICs, Nordic ICs, and they've publicly stated that they want to go into the energy harvesting market. But I don't know by heart, and I'm not, I'm not really an expert myself into the lower layers or the power domains, etc. The technology. I'm more of on the software kind side of things. So I cannot answer or give you a proper answer, but I could, if you want, send you a few links.
Yeah, that would be great. I would like that very much. Yeah, that would be really great.
Sure.
And I want to give somebody else a chance to ask a question.
Does anybody else have one? We miss anything on?
No, I know somebody who does.
Yeah, Michael.
I have a question, but it's more general, not so much about BLE, but it's more generally about Bluetooth-related audio. And it has to do with more with codecs. I was early in wanting wireless audio devices capable of better quality than telephony was typically delivering, and I see now stuff with technology from a company. It's branded APT-X, and I was wondering if there are varying implementations of this, because I've purchased something and I thought, it wasn't really living up to my expectations. And are there any facilities within the standards that allow for really good, musical quality audio, or is it more video conferencing, which is sort of traditional wide, and then there's narrow band. Obviously, was where it all started.
Yep.
But I'm
So,
curious.
yep. Yeah, sure. So there are two ways of transferring audio over classical Bluetooth, the standard Bluetooth. One is what they called SCO, which is essentially the same as one of those USB synchronous pipes. So those are packets that go at regular intervals and contain data, control audio data, which is sampled directly and typically not even filtered, just sent directly. And then that is what, for example, hands-free car kits and headsets, etc., mono type data sources of audio use. Then there's the A2DP, which is a streaming protocol, which is simply a transport mechanism. So it defines the flow control mechanisms and the reliability of the transport. It defines the packet formats, and it defines as well the connection procedures and the pausing procedures, even things like it goes beyond that with an additional profile to define things like control of the audio stream, such as pause, skip, and even gallery art for the source of the audio. Now,
Carlos,
yeah.
I have to interrupt you because my connection dropped or something. When I dropped out of the call, you are actually in charge.
Am I? Okay.
Take a look. I know you have to go soon too, but take a look at on the flyover menu, you should see a telephone icon on the right.
Yes, I see that. Yes.
So if you could click that, and there's a SIP URI, and you should be able to just call that the one that's filled in.
Okay.
And us to the bridge, if you would.
I'm doing that now. Yeah.
Yeah, and then then you can go ahead.
Connected. Yeah.
Now joining in wideband.
Okay.
Now muted.
After
Press star 6 to unmute.
Okay, we just
13
need
other participants.
to unmute that. Okay.
You are now unmuted.
Okay, so we're good. I'm sorry for the interruption. That was, I guess, my connection. So please go ahead.
Okay, that's okay. So so I was talking about A2DP and how it provides a mechanism and a framework to transfer audio data, but that audio data cannot be uncompressed. It has to be compressed by a codec. So aptX is a codec, and it's a codec that was developed, it's a proprietary codec. It's not part of the spec. The spec does provide a standard codec called SBC, which has no royalties, no patents behind it, and it's completely free to use. Unfortunately, SBC is not very, or I'm told, because I'm not an audiophile myself, but it's not very good for streaming. But going back to the question, which whether Bluetooth is suitable for the types of high-end musical audio, the answer is in general yes, as long as you can put up with compressed audio. So the typical bit rates for Bluetooth audio range from 100 to 400 kilobits per second. So that is a range that's usually acceptable in terms of compressed audio. And in fact, there are many sound systems out there using or accepting Bluetooth audio. That goes when you connect two Bluetooth A2DP enabled devices. The first thing they do, one of the first things they do is to expose the codecs they both support. So that could be MP3, that could be AAC. That could be as well SBC, which is the standard and usually must be supported, and that could be aptX as well. So aptX is designed to provide good quality audio with minimal bandwidth, and I, however, do not have more knowledge about aptX itself. I've never worked with it, and but I'm sure they have a lot of information on the website though. But in terms of what these type of application, what A2DP is geared towards, it really is stereo audio of mid-range quality. So again, between 100 and 400 kilobits per second of compressed audio. So
okay,
even
thank
more.
you. One of the things that I've encountered is it was just as you shift, as a user, if you're using a mobile device of some description, and you go from a wired connection to a wireless connection, you get convenience, but you are actually giving up something, and depending upon what your use case is, it may be noticeable or it may be offensive, but it seems one has to be careful in the devices one buys is all. So
You are, but the thing is, the thing with A2DP is that it's been extremely popular on mobile phones to stream audio to either a car hi-fi system or to a pair of stereo headsets that support it. And the reason behind that is that yes, you do lose potentially quality, but in fact, what happens today is that there's no transcoding most of the time. Also to save power on the phone side, what they do is, because typically people in general, customers or users have their music already encoded in a format that's compatible with the standard, with the Bluetooth standard, such as AAC or MP3. What they do is they essentially just take the data from the file and just stream it over Bluetooth, and it's up to the decoder at the end to transform that into an analog signal and decode the MP3. So or AAC. So it becomes a transport layer that's capable of sending those files in a way that obviously they can drop packets if and they're synchronized with video if necessary, etc., etc. But in the end, it's that's how most of these transactions go. However, aptX was designed specifically for Bluetooth, and therefore sometimes it is a worthwhile trade-off to decode your AAC into raw PCM, raw uncompressed audio, then go back to aptX and then stream it, because the final result, depending on the on the noise and the ambient noise, on the radio noise, it could actually be better. And obviously, if you're, for example, generating the audio in real time, because you have to take into account that what happens today in a modern mobile phone as well is that you've got a mixer. So you've got your MP3, but you've got also, sometimes you want to add to that some system sounds or perhaps a Skype call, and everything has to go over Bluetooth. So if you're doing that, you obviously need to then first mix all of the sources into uncompressed audio, then compress it, and then send it over. And at that point, if you use aptX, you're using a codec that's tailored to the Bluetooth radio. Now, if you are only listening to music, and many phones up until now that implementations I know did this, if you're exclusively listening to music, it will send in the native format. And it's at the point where you have to mix sounds that they switch codecs. I've seen that in several instances. I'm not sure if this is still the case. This was a few years ago.
excellent.
Yeah, I think we're running pretty late here. I think Carlos has other things he wants to do. If nothing else, he has a life like I do. I have dinner waiting for me. Any final questions? Anything that we didn't get to that we should have? Anyone? Otherwise, I'm going to ask Carlos the same question. Last night, I installed Windows 8. I don't know. That doesn't seem to have anything to do with anything. Is there anything we haven't said, Carlos, about the book? Or we have two winners, by the way, and I'll announce those in just a second. Is there anything that you wanted to mention that you have not been able to, though?
No, just a couple of words about the book then, since I barely mentioned, just that it's basically essentially this written for engineers that want to start a project in Bluetooth Low Energy. So if that's something you intend to do in the future, you could consider the book, because it's written in a way that assumes certain engineering knowledge, but that's about it. The rest is introducing you to the stack, to the protocol stack, and then to the APIs that you can use both on the embedded side, and we cover most popular vendors, because there's a few. We cover us, but also the others. And then on the mobile phone side, we try to cover both Android and iOS in a way that allows you to write a simple app to test your sensors or devices or automation mechanisms or whatever you want to do.
Okay, Carlos, thank you very much. This has been really a fascinating call. You know your stuff, and please keep in touch. And if there's anything new on any of the things you're doing, we'd love to hear from you. And if you feel like dropping in on any of our other sessions, of course, obviously, you'd be very welcome.
Thanks very much, and thanks for having me, and it was a pleasure.
It was great to have you, Carlos. I just should probably announce that Mr. Carl Pfeif, Mr. Last Question, has been one of the great winners. We only had two people, so it was perfect. It was easy. I didn't have to do the random number thing that I had set up. Carl Pfeif and Phone Buff. So those are our two winners. Thanks to O'Reilly for helping us out. And again, thanks to you, Carlos. This book looks terrific. I haven't had a chance to look at it because I got it kind of late, but it's exactly what you need if you're into BLE. So go for it.
Thanks very much.
Thanks, everybody who participates. I'm going to have to check.